Welcome to my talk on synthesis from weighted specifications with partial domains over finite words. This is joint work with Emanuel Fidio and Christoph Löding. This talk is about synthesis. In synthesis, we have a specification where one input is in relation with several outputs, and the goal is to synthesize an implementation, which is a function that selects a unique input for each output, such that the input-output pair is part of the specification. And here we are interested in specifications and implementations given by automata. We consider specifications given by synchronous deterministic automata. These are automata that read on each transition two letters, one input and one output letter. For example, here we read an input A with output C, here we read input A with output D, and in order to reach a final state, we have to read input B with output D, and the same here. So the domain of this specification are all words that start with an arbitrary number of A and are followed by a single B. So what kind of implementations are we looking for? We are looking for implementations given by synchronous sequential transducers. These are deterministic automata that on each computation step read exactly one input and produce exactly one output letter. For example, this transducer here, if it reads an A, it produces a C, and if it reads a B, it produces a D. Let's check that it is indeed an implementation of the specification. You can see that this transducer here directly corresponds to the left-hand part of the specification, and it has the same domain as the specification, an arbitrary number of A's followed by a single B. Another transducer is this one. For every letter, the output is D. This is also an implementation of the specification. Here we can combine A with D, and B with D, and accept. So now we have two implementations of the specification. But which one is better? So this is the goal of this talk, giving quality to specifications. How can we add quality to implementations? If we have a specification, then we can synthesize different implementations, and each implementation is basically just a collection of execution sequences of the system. So now, if we add a quality measure, which is a function that assigns to these execution sequences a value, then we can combine these with the specification, and now if we synthesize implementations, each of the execution sequences is also assigned a value. So this allows us to talk about low and high quality implementations, and the goal is to rule out low quality implementations. So, but what exactly does it mean that an implementation is low or high quality? So how to define high quality? There are several ideas. For example, one could say all executions must have a lower bounded quality, meaning that all executions that are part of the implementation, that the quality of it is greater or equal to a given threshold. Another idea would be to ask for quality optimal executions, meaning that for every execution that is in the implementation, its quality should be the supremum of all qualities for executions that have the same input sequence. Also, if we are not looking for quality optimal executions, we can look for executions that are almost quality optimal, meaning that the gap between the achieved quality for an execution and the optimal quality that can be achieved for the same input must be smaller or equal a given threshold. So, how do we combine a specification and a quality measure? Then we have weighted specifications. These are synchronous deterministic automata with weights. We simply give integer weights to the transitions. And now we have a way to assign values to runs of the automaton. So the value that we assign to a run of the automaton, it depends on the use payoff function. For example, if we use sum and take a look at this run, AC, AD, BD, AC, AD, BD, the sum is 2. And the run ACADBD, it corresponds to the pair with input AAB and output CDD. So what happens to pairs that do not have a run in the automaton, which are not accepted? The value of this pair is always minus infinity. And so the domain is defined as all inputs where there is an output such that this pair has an accepting run in the automaton, meaning that the value assigned to this pair is a rational number. And we call an input valid if it's from the domain. And as we've seen earlier, for this particular example automaton, the specification domain is an arbitrary number of A's followed by a B. Okay, let's take a look at the first quantitative synthesis problem, threshold synthesis. In the threshold synthesis problem, we ask that we have an implementation that satisfies for all valid inputs that the achieved value is greater or equal to a given threshold. So let's take a look at an example. Again, this is the same automaton. Let's interpret it as a sum specification. And here we have one implementation. It's the implementation where the output letter is always D. Okay, what does it achieve? This implementation ensures a value of at least 3 for all pairs. For the input B, the only possible output is D, so we achieve a value of 6. And for all inputs starting with A, the output is always D, meaning we take runs in the automaton going here to the right-hand side, possibly looping here, and then eventually going to the final states. And the sum of these runs is always greater or equal to 3. And what should happen on invalid inputs? The implementation can do anything on it. Okay, so these are our results for the threshold synthesis problem. We studied it for specifications given by synchronous deterministic sum automata, average automata, and discounted sum automata. These are the achieved complexity results. Okay, but how did we solve it? The idea is to see it as a game problem between two players, Adam and Eve. Adam should provide input and Eve should provide output. They should alternate. And the combination of input-output should be in the specification, and it should additionally satisfy some quality constraint. How did we do it more concretely? We introduce a new type of games, critical prefix games. Critical prefix games are a general type of game tailored to model synthesis problems with finite inputs and partial domains, just as we consider here in this talk. So how do critical prefix games look like? A critical prefix game is an infinite iteration 2-player turn-based weighted game with critical vertices. And when a play is in a critical vertex, then quantitative constraints on the prefix are checked. And when these constraints are fulfilled, then the play continues, and otherwise Adam wins. And when the play is not in a critical vertex, then nothing has to be checked. The idea to model our synthesis problems with critical prefix games is to ensure that whenever a play prefix corresponds to a valid input sequence, that the play must be in a critical vertex. And whenever the play prefix does not correspond to a valid input, then the game should not be in a critical vertex. Okay, so in this way we can model our threshold synthesis problem as critical prefix games with threshold conditions. And we show for critical prefix games with threshold conditions that these are decidable for sum, average, and discounted sum payoffs. How do we do it? For sum and average critical prefix games, we show that these reduce to mean payoff games. And if we consider discounted sum critical prefix games, these reduce to discounted sum games. The next way to judge the quality of an implementation was best value, and in the best value synthesis problem we ask that the achieved value of a foreign input by the implementation should be equal to the best achievable value for the input. Okay, let's take a look. This is again the same specification, and let's interpret it as a sum specification and see what are the best values that we can obtain for the inputs. For input B, the best value is 6 by combining it with D, also the only possibility. Then the best value for AB is 5. This is achieved by taking this run, ACBD, which is 5. Then for AAB, the best value is 4. It can be achieved by 2 different runs. We can take the run AC, ACBD, which is 4, or we can take the run AD, ADBD, which is also 4. And then if we have 3 or more A's, in order to achieve the highest sum possible, we have to output always D, and then the runs that give the best value will be AD, possibly more ADs, and then BD. Okay, and from this, it is rather easy to see that no best value implementation exists, because assume we have an implementation and the first letter is A, then we don't know if the output should be C or if the output should be D, because this depends on the number of A's that are yet to come, which is unknown. So no best value implementation can exist. These are the results for the best value synthesis problem. Again, we considered specifications given by deterministic synchronous sum automata, average automata, and discounted sum automata. For sum and average automata, this was already known. For sum payoff, the result is obtained by a reduction to another problem, namely to the problem of determinization by pruning of non-deterministic sum automata. That means you have a non-deterministic sum automaton, and the goal is to find a deterministic subautomaton of this non-deterministic one that generates the same weighted language. And then for average, this reduces to the sum case. We will later see how. And for discounted sum, we show a reduction to a discounted sum game. Then lastly, we considered the approximate synthesis problem, where we want that the gap between the achieved value of an implementation and the best achievable value for some input U is smaller or equal to a given threshold. So again, we take a look at the same specification and interpret it as a sum specification. And now we have this transducer here. Let's check that it is indeed an implementation. So for B, the output is D, which is here, BD. And then for the first A, we have output C. And then for all consecutive A's, we have output D. And then finally, we have input D with output D. Input B with output D. So here in this automaton for A's, the first A is combined with a C. Then we can have ADs, a number of ADs, and then BD. So how good does this, we have seen that this sum specification, that no best value implementation exists, but let's see how good this implementation approximates the best value implementation, and this one ensures a value of at most to less than the best value. Here we have the values achieved by the implementation, and here we have the best achievable values that are possible for the input. We see that for B and AB, the achieved value and the best value, they are the same. And if we have input words that have 2 or more A's, we see that the difference between the best value and the achieved value is exactly 2. Because the implementation, what it does, for the first A, it produces a C, and then for the other ones, it produces D until it finally sees the B produces a D and accepts. So the value of these runs will be I, and the best sum for inputs of this form can be achieved by directly producing a D already in the first step. So the runs will be of this form, AD, more ADs, and then BD, which leads to the accepting state. So we have a difference of 2 between the runs for I is greater or equal to 2. So these are the results, again studied for sum, average, and discounted sum automata. For sum, this problem was already known. It can be reduced to regret determinization of sum automata. For a discounted sum, the problem is open in general, but if we have a discount factor that are of the form 1 divided by n, and n is an integer, then we can reduce this problem to discounted sum games. And for average, we have seen 2 slides before that the best value synthesis problem reduces to sum, but this is no longer the case for approximate synthesis. So we will take a look at how best value, average, and sum, how they reduce to each other, and why it's no longer true for approximate synthesis. And then go into the proof idea for average. Okay, so this is the condition for approximate synthesis with average payoff. The gap between the best achievable average value for an input u and the achieved average value for an input u should be smaller or equal to a given threshold. If we formulate this as sum, then we have to compute the sum value divided by the length of the run, compute the sum value of a run divided by the length, and then we arrive at this term here. And now if we compare best and approximate synthesis is best value synthesis if the threshold C here is 0. So from 0 we have this equivalence here, and so it's easy to see that for best synthesis, average and sum can be reduced to each other. So let's take a look again at the specification and implementation from the approximate synthesis case. We have considered it as a sum specification, and we saw that if we have inputs that start with at least 2 a's, then the difference between the achieved sum and the optimal sum was 2. And if we now interpret this automaton as an average automaton, then we see that the longer the inputs get, the more a's we have, that the gap between the optimal average value achievable and the achieved average value goes to 0. So you see that it is interesting to consider both sum and average as payoff measures. So how did we solve the problem? This problem we could also reduce to our new concept of critical prefix games. And what we did is we reduced this to a special type of critical prefix games with imperfect informations. And these games reduce to imperfect information games with fixed initial credit, which is a decidable class of imperfect information games. So this is an overview over the results. In the rows, you find the problem description. In the columns, you find the type of specification considered, deterministic, synchronous sum, average, or dsum automata, and the corresponding complexity results. So the already known results, the references for that are these 2 papers. So, and for future work, it could be interesting to study these problems not only for deterministic weighted finite automata, but also for specifications given by unambiguous or non-deterministic weighted finite automata. Thank you.